Ladies and gentlemen, my name is Tom Kitchen, and for 20 years of my life, I was in the United States Navy as a Navy molder. What's a molder, you ask? Well, it's also known as a foundryman on the outside. And what we did in the Navy, as they do on the outside, we make molds, make cores, pour, operate the furnaces, pour molten metal into the molds, prepare the molds for machining if need be in the ship's machine shop, and send other things off to the customers who wanted them. Now, I was born in Vallejo, California. I lived there for a short time, like 1 year, and then we moved to Orangevale, California, in the Sacramento Valley, and then somewhere halfway through my high school time, we moved to Citrus Heights, California. I graduated from high school and then joined the United States Navy. Went through 16 weeks of boot camp. Went through 16 weeks of Molder A school. A school in the Navy being the school that you would go to teach you the least sophisticated information of a particular job, just your basic talents. And but it's certainly 16 weeks is certainly enough time to teach you most everything you would ever learn when you're in the Navy, in the Navy foundries. Anyway, after I graduated from Molder A school, I went to my first command, the USS Fulton, AS-11, AS being submarine tender, out of New London, Connecticut. Got transferred to the USS Piedmont, AD-17, AD being a destroyer tender. Did my 5 years of sea duty between the two commands. Went to San Diego, 32nd Street base in San Diego, to the foundry there. Learned a bunch there because we had enough room to do almost anything. And also at that time that I was in San Diego, they let me go through Molder J school, which in the past was called Molder C school, but they were at the time going through a political change in the Navy where they were trying to make the C schools into J schools, J being short for journeyman. Okay, so that if we got out, we could say, hey, I'm a journeyman level, have journeyman level training, and maybe we might get more money if we was able to claim that. That's my supposition. Anyway, got San Diego done. Went to the USS Sierra out of Charleston, South Carolina, and the Sierra being AD-18. Got 5 years on the USS Sierra completed. I put in for and was allowed to go to the EEAP program, which means Enlisted Educational Advancement Program. And what that program was back then was it allowed you to go to a college, and most likely a lower grade college, because it was mostly to teach you what you needed to know that was in relation to your trade. So it'd be a technical college that you'd normally go to get that kind of information. Anyway, went to that. To the Thames Valley State Technical College in Norwich, Connecticut. Graduated with honors there, and was sent to the USS Yosemite to spend the rest of my time in the Navy. Now, the kind of things we made on these ships, on the USS Fulton, we made a lot of plaques, a lot of andirons, mostly decorative things, because the stuff you had to, and this being a submarine tender, if you made anything, created anything for the submarines, it had to go through the subsafe system, which is way far and above what we were able to, go to at that point in time, being a small foundry and having, none of the stuff we needed to prove what kind of materials we were using and how well we were doing it and all that stuff. You needed that back then. But I understand now there are some ASs that are able to qualify for the SubSafe program and are doing well in that, or actually they did well when they existed. Bravo to you guys. On the ADs, the destroyer tenders, when we still made plaques, okay, because we had a lot of commands that had a call for plaques to give out to the people who would be retiring or who would be re-enlisting. It was a big morale thing. So we still made plaques, but we also made a lot of the structural things on board ships, like the watertight door dogs and some small pump bodies and mechanical things like that. We enjoyed that a little bit more than plaques, I think. We were able to showcase our capabilities a little bit better doing that. But, that's the way it was in the Navy. They really didn't know what we could do, and it took a lot of effort on our part to try and prove it to them whenever the occasion came up. Now, a comparison of the civilian foundry versus the Navy foundry. In the civilian foundry, let's say you get, you graduate from high school and you're looking for a job. There's a foundry in your area, and they have some openings. Now, being the low man on the totem pole, or low lady on the totem pole, you're most likely going to be put in there to clean up, and so that you can be exposed to the technology, in that area. Well, eventually there's going to be an opening, and if there's an opening, and you're qualified to fill that space, they're going to put you in there. But most likely they'll put you in there until you retire, because once there are so many different things in the foundry trade that that a civilian foundry simply has no time to put you through the training that's needed to be able to do all of that. They're more oriented towards getting the profit. The profit means putting out lots of castings, and that doesn't help when you don't know what to do. So they'll teach you one thing, maybe two things, ordinarily, and that's where you'll stay until you retire, unless you on your own learn the different aspects of the foundry trade. Navy though, 16 weeks, they teach you everything. How to make molds, the different ways you can make molds, gating systems, different flasks that you use to make molds in, making cores for molds, making operating the furnaces, pouring teams, everything you can think of that takes place in a small foundry, they teach you how to do it. And well, in addition, I haven't seen very many of these videos going on, but in addition, beside the actually making castings, there were two other capabilities that the Navy taught you, and one of them is to re-pour wire rope sockets and to repair Babbitt bearings. So, and I'll cover that information too somewhere along the line in this. So it's a very different thing. It was a very different thing. I keep forgetting that they don't have the molders anymore in the Navy, but it was a very different thing back when the molders existed, between the capabilities of a Navy molder and the capabilities of a civilian foundry operator. But does that mean I'm an expert? No. Nobody's an expert. And here's an example. If you ever come across somebody that says, I'm a karate expert, despite the fact that he's a black belt, you've got to believe that he can't be an expert. Look how many different types of or schools of karate there are. Nobody's an expert in karate. Everybody in the art of karate continues to learn until they die of old age. Everybody always learns. There's too much out there. Somebody comes along and say, I'm a medical expert. No. No, you're not going they're not going to be a medical expert. There's too many things to learn in the science of medicine for any one person to be an expert in medicine. Okay? So beware of those people who say they're an expert in anything. Okay? I'm experienced. Okay, I started off as a MLFR, a fireman recruit molder, coming out of Molder A School. And over time, I finally made chief molder, chief petty officer molder in the United States Navy. That doesn't make me an expert. That makes me experienced. Anybody in any foundry, no matter what rank you are, you become experienced quick like, because even the guys who are at the top of the ranking in the shop, they're going to know more, and they're going to help you if you hit a stumbling block when you're trying to make something. But you're going to learn real quick on how to do a whole lot, and you'll become experienced in the foundry trade. Well, this is what I intend on doing. It's almost going to be as if I'm receiving a person out of high school on board the ship. You haven't even gone through Molder A School. They don't have. I'm not sure if nowadays they even have A schools. I've understood from other people that a lot of that training has gone away. So it wouldn't be too far fetched for me to pretend that I'm a chief in a shop, and I've just had some guy or gal come from boot camp, and I'm supposed to train that person how to do their job in the foundry. Well, I'm going to pretend that you're that person. You know nothing about the foundry trade. So me having to start off at that level, if you know more than that, please, have patience. In time, I'm going to be covering stuff that you may not have learned. Okay? And, my intent, in the beginning, in this video right here, what I'm doing is just letting you know who I am, letting you know basically my background in the foundry trade. And this video is going to go to, kind of ancient history to kind of give you an idea how far along humankind has gone to get to where we are now in the foundry trade. All right, so from this point on, I'll be using a lot of the information off the internet, rather a lot of the photographs and drawings and things that they have on the internet to try and illustrate what I'm talking about. Now, the reason why that is I'm retired. I no longer have access to a foundry. I can't show you how to operate the furnace. I can't, physically show you how to make cores yet. I can't physically show you how to make molds yet again. I intend on trying to gather the materials required and the equipment required to do that, so that somewhere along the line I can show you exactly what I'm talking about. But in the meantime, I'm going to give you drawings and photographs, and maybe even a little bit of drawing of my own on a whiteboard to illustrate what I'm speaking of when I cover a particular subject matter. Okay? So, without further ado, let me take you back in time. Now, I'm not a history professor, but I've always been very interested in archaeology and anthropology. This is not going to be a history series, But if you're going to understand how the foundry industry was invented and how it grew, you've got to know a bit about how humans first discovered metal and how they worked with it. Keep in mind that all these facts and figures I'm about to present come from archaeological digs. So the facts change as time passes and we learn more about the human experience. If you happen to disagree with any of these facts presented to you, I suggest you look them up, really educate yourself, and then present your objections. I'm a molder, not a professional teacher, and certainly not a professor in archaeology or anthropology. Sometime between 50,000 and 100,000 years ago, humans of the time started to drift out of Africa and spread out to the habitable countryside in the Middle East. At this point in time, the humans were still hunter-gatherers and had to follow the herds and gather the food as they found it. Approximately 11,500 years ago, some genius in some tribe in Mesopotamia discovered that he could gather the seeds of the things he ate, plant the seeds, and grow the crops themselves, not relying on Mother Nature to provide on random bushes. Of course, this required the previously nomadic tribes to stay where they could grow the food, so a major shift in their lifestyle was made. They went from a hand-to-mouth existence, where they starved most of the time, to an existence where they could grow much more than they could eat. In addition, they also learned how to domesticate animals for food and became herders, allowing them to have a constant source of food. Sometime approximately 11,000 years ago, in northern Mesopotamia, a sharp-eyed individual found an outcropping of green-covered material and took some of the chunks of material back to his hut and played with it until a green verdigris was removed and the copper metal was exposed for the first time in human history. Presumably using a hammer made of stone, or just a hand-held stone, the tribesman played with the material and found that it was soft enough to be formed into whatever shape he wanted, and that, if you rubbed it enough, it could become shiny and therefore very attractive to the ladies. This is only a guess on my part. While that may have been a tongue-in-cheek comment, it is absolute fact that shortly after the discovery of the very first metal to be used by humans, decorative beads were made and worn as necklaces by women, which were buried with them when they died, and thousands of years later found by archaeologists. That tribesman had found the very first metal to be used by human beings on this earth, and a great many things were made of this material, but mostly the things were decorative. Copper, in its natural state, is very soft, and you can dig copper right out of the ground if you're able to find a copper deposit. So once the copper deposit was discovered, and the fact that you could work the copper into different shapes was found out, the mining industry was born. Now, metal was a very new concept to human beings. They already knew how to work with wood, how to use all the materials supplied by animals, and how to work with stone, but they had never worked with metal and had no idea how to use it properly. Of course, the very first things made of metal were the things that could be most easily be produced by simple pounding by rocks and smoothing with sand and eventually rubbing shiny with their fingers like jewelry and distorted mirrors. You've got to presume, though, that someone, most likely a hunter or protector of the tribe, tried to make an axe or a knife out of the material and was thoroughly disappointed in the results. It would be easy to imagine that once the axe or knife was used and the sharp edge dulled beyond use, that the disappointed hunter/warrior would have thrown the device to the ground and walked away. You should know that during that time in Mesopotamia, now known as Iraq, it was not the desert land that we know today. The establishment of agriculture and horticulture was well before the time when the monsoon rains falling on North Africa shifted south, and well before the tropical trees, like the palm tree, started to decrease and the desert plants started to take root in the part of the world that we now know as the Sahara Desert. The Sahara Desert back then was a grassy plain, having many tropical trees growing in it
having numerous rivers flowing from the area of the Nile River west to western Africa. Mesopotamia was well suited for agriculture, being very green and having occasional rains to supply the rivers flowing through it. The dry weather didn't turn northern Africa into desert until approximately 8,000 years ago. It took a while for the population to grow after the huge sociological change from hunter-gatherers to farmer and herdsmen, but eventually villages were established, and sometime approximately 7,000 years ago, city-states were starting to be established. It would never have occurred to the men of the time that you could put something in fire and still be able to use it afterwards. Keep in mind, anything except stone, perhaps, that they had put in the fire was destroyed by the fire. Copper was a very rare and precious material in the beginning, and no one could have even imagined that you would want to put copper in a fire. So it took almost 4,000 years for some accident to take place that introduced copper to a heat source and opened the door to an infinity of possibilities. Archaeologists, while excavating Babylon, discovered evidence of early refining of the copper and smelting of iron. It is obvious that the Babylonians had made the leap from simple pounding on the copper to melting the metal so that a pure form could be made. You would think that once the Mesopotamians discovered that they could work with metal in fire and make many more things, that industry would have taken off and their lives would have been made much easier afterwards. But don't forget, they didn't have the modern equipment needed for mining. They didn't even have metal yet that could be used as chisels or hammers or pry bars, something needed in a mine. All they had was stone and a very small number of animals that could haul ore back to the place where the metal was being worked. The wheel wouldn't even be invented in Mesopotamia for 2,000 years after the discovery of copper. So imagine the expense of trying to gather raw ore and deliver it back to the village. Also, the Mesopotamians didn't have forests like Europe, and the hardwoods required to make charcoal or have coal mines in the area. Materials required to make hot fires and melt either copper or the newly discovered metal iron. The workmen had to settle for softening the metal to be worked until about 7,000 years ago, when tin was accidentally discovered and the Bronze Age started. You should know that tin doesn't occur as ore in the ground like copper ore or iron ore, but as a compound called cassiterite, where it occurs as tin dioxide and is found typically formed in granite rock. Little wonder it took so long for the Bronze Age to occur. As time progressed and humans left the ancient human settlements, they took the secret of metal working with them. Great strides were made in making and using metal once a constant source of fuel was found to heat their furnaces. The good news was that after hundreds of years of developing the use of metal, the living conditions of both the nobles and the common man improved due to the manufacturing of cooking implements, building implements, and material handling equipment like the cart. The bad news was that the weapons of war also became better, and killing your neighbor's city-state became easier and more effective. Time progressed, the pages of human history turned, and suddenly the Roman Empire was in charge of most of the known world. Along with a brutal system of government, the Romans also exported the Roman way of engineering. This improved the overall conditions of living for the conquered areas, and the locals learned much from the people who made the Nazis look like inept bullies. And then came the Dark Ages, with the fall of the only effective government in the Western world in the 6th century, and the terror of the bubonic plague, also known as the Black Death, in the 12th century, a horror that killed 1/3 of the European population, estimated at 20 million people. The jealously guarded knowledge of metalworking died out along with the population, and the people reverted to living as their ancestors did, in ignorance, superstition, disease, and starvation. Finally, dragging the people out of the muck and mire, the Italian Renaissance was born in the 14th century, and eventually the British Industrial Revolution in the late 18th century, where the true history of the modern foundry industry was born, and where we still use tried and true techniques in molding and melting metal developed back then. In fact, a great many of the vlogs I've watched remind me of the same halting steps our ancestors must have made when they experimented with various ways in melting metal and in making molds using the materials they had at hand. The American spirit of self-reliance is reasserting itself, and I intend to spread the knowledge that I've learned since I became a molder, with emphasis on using equipment and supplies that, while not the latest and greatest, would have been immediately recognizable by the foundrymen 200 years ago. Now, a short lecture on the basic molder's tools and how they are used. The first thing in the morning, after getting into uniform and attending quarters, we would receive our assignments and start to gather the equipment we would need to ram up the molds needed for that day's pour. This is a drawing showing a well-planned molding bench, the top of which is at the molder's belt line. The bottom is recessed so that the molder's toes aren't hitting the bench, and the flask is sitting on a pair of rails so that the sand that falls out of the flask during the molding process will naturally fall into the sand pit and not all over the floor. 90% of the time, the flasks we used were snap flasks. When you finished your mold, you would move a set of levers or open a set of locks that had held the flask in a closed position while molding. Once opened, it would provide a large enough gap around the mold so that the flask could be removed and the mold be placed on the pouring deck. This is an all-metal flask that opens when the levers on the near and far corners are shifted to the open position. The flask will then have enough of a gap around the mold itself that the flask can be lifted straight up and away from the mold, and the mold be placed on the pouring deck. This is a wooden flask, as you can tell by the box joints used on the two immovable corners. In this case, once the mold is finished, the locks you see at the nearest corner are unlatched, and the flask allowed to open because of a set of hinges installed on the far corner. Both flasks have hardware on the sides that ensure the two halves can be taken apart and put back together during the molding process in such a way that the sides of the mold are undamaged. This person is showing how the wooden flask can be removed once the mold is completed. Keep in mind that one must be careful removing the flask, as you can easily brush against the side of the mold and damage the mold. This should, however, never be real concern, because you should have at least an inch or an inch and a half of sand between the mold cavity and the outside edge of the mold. I should point out a couple of problems that I see in this picture that make me cringe every time I look at it. The first problem is that there are no sprue covers on the molds to prevent water or contaminants from entering the mold cavity. The second problem is that it looks as though the molds are being placed directly on the floor and not on any molding boards. This is a molding board. The molding board keeps the mold off of the floor and away from hidden sources of water that could be drawn into the mold like a wick and possibly cause a steam explosion within the mold. This scenario is especially problematic when you're using water-based green molding sand. If you're using Petrobond sand, however, it's less of a problem, as the Petrobond sand is an oil-based sand and won't draw moisture into the mold, even if sitting on top of some. In addition, the bottom board, being constructed of thick wood, will prevent the mold from conforming to the pouring deck's shape, which would most likely cause the mold to split not only allowing the casting to be damaged, but also allowing the possibility of molten metal to flow out of the crack onto the pouring deck that, if made of wood, might catch fire, or if made of concrete, which could have absorbed water in the past, could explode once the molten metal heats up the water within the concrete and turns it to steam. The steam will then explode under the molten metal, scattering the metal around the pouring deck, possibly causing something to catch fire and also likely damage the pouring deck, making small craters in the cement. These are pneumatic rammers. Like the hand rammer, these rammers are used to ram molding sand around the pattern so that the castings can be made. These rammers have butt attachments installed on the rammer's shaft, but peen attachments can also be installed on the rod, which is what we used when making molds. The one on the far left was used on the bench, being small and easily used with one hand. The others were normally used on floor molds, where more force was likely needed. These hand tools are called fillet irons, and were normally used by pattern makers to attach leather or hard wax fillets to patterns where 90-degree angles needed to be softened. As a molder, I used them to smooth out the sand where I constructed my gating systems, including the pouring basin, splash basin, runners, and end gates. These are a small collection of hand tools for the molder. Of course, the hand rammer on top is recognizable to most, with the butt or flat part being on one end and the peen or wedge-shaped part being on the other end. The two outside tools are trowels, which are used to smooth large areas of sand if need be. The bottom tool is a lifter, used to recover chunks of sand in deep holes, or used to smooth defects at the bottom of deep holes and mold cavities. The 5 remaining tools in the center are examples of double enders. The double ender is used to repair sand defects found in mold cavities, or used to cut gating systems into the molds. The standard double ender has on one end of the tool a spoon-shaped part used to smooth out curved portions of the mold, and the other end is typically a flat piece of metal, smaller than a trowel, that can repair defects on flat portions of the mold cavity. This is a page from a catalog dated in the late 1930s, showing some of the many combinations of shapes that could be utilized on double enders. As you can see, the craftsman in need of a double ender has his choice of combinations and could easily buy the tool needed for a specific job unique to his job or the company. This gentleman appears to be nearly finished with that particular mold, as he is using the butt end of the hand rammer on the final layers at the top of the mold, and he's ramming the sand around the 2 wooden rods being rammed up in the cope, as it appears he is using steel flask, examples of which can be seen in the foreground. But I have no idea why he's using 2 hand rammers at one time. Lacking any clues to what he's actually making, I can guess a little bit of what's going on. The 1 wooden rod near the corner would likely be the sprue, as this pouring basin can easily be constructed there, and the other rod could likely be a small open riser. This is essentially what you would see on the pouring deck in the Navy Foundry, waiting to be poured, minus the extreme angles of the side of the mold. Normally this draft of the side of the mold would be no greater than 5 degrees. I've explained the bottom board's use, but not the jacket and the mold weight's use. The jacket covers the seam of the 2 mold halves and keeps them from moving in a side-to-side direction if accidentally, impacted upon. The mold weight is placed on top of the mold and will hopefully exert the force necessary to counter any hydraulic lift exerted on the cope by the molten metal as it comes in contact with the cope. If a steel flask is being used as in the case of a floor mold, mold clamps will be used to keep the steel halves of the mold from moving during the pouring segment of the process. This is a floor mold. It is too large and heavy to be worked on the bench, so everything has to be done on the floor. You can see the bottom board that it's sitting on and the steel flask in which the mold cavity has been constructed. In between the handles, you can see mold clamps in place, but you can also see the molder found it necessary to place mold weights on top of the mold. Placing mold weights on top of the mold when mold clamps are in place is redundant and not normally done. The only reason I can guess that the mold weights were put there would be to counter the possibility that hydraulic pressure would press against a thin portion of the mold cavity and possibly cause the mold cavity to be distorted. This distortion would likely make a crack in the mold cavity that would allow the molten metal to pour out onto the surrounding pouring deck, causing the aforementioned destructive results. On the upper left portion of the mold, you can see a pouring block used to not only act as a skimming tool and a pouring basin, mitigating the problems with splashing the molten metal, but is also used to increase the head height of the metal column, with the final result being more hydraulic pressure in the gating system, which would feed portions of castings that are well above the mold's parting line.